So what we are looking at today is what's called a power function. When you guys are studying quadratics or cubic functions, that is actually a specific type of power function. A function that is considered a power function is just any function that can be written in the form f of x equals k times x to an a power. Couple quick things here. K cannot equal 0 because if k did equal 0, that whole equation would be wiped out. And then also a cannot equal 0. So those two things can't equal 0. It's not a huge teaching point, but it's just something to take note of. Some things as far as like the different parts of this function. So k is considered your constant of variation. Oops. Constant of variation. And your a is considered your power. All right. So the way that you would read this is that your function or your f of x varies as the eighth power of x. So you may have seen something similar to this in the past with this constant of variation. If you guys ever talked about varies directly or varies indirectly, you may have seen that in some class prior. The other way that you could read this or that you could look at this is that the f of x is proportional to the eighth. When I say eighth, that is a and then th, eighth power of x. So what we're going to look at today is first off analyzing your functions and kind of what they look like, and then also being able to write statements using power functions. So here's the thing. When you are analyzing power functions, you have a lot of things to be looking at. And so I'm not going to read all of them, but you are going to analyze all of those things. And so here's the thing. How can your leading coefficient and power help determine some of the components of analyzing? So if we talk about things that we already know, so we're going to look at positive powers. Okay, if it is an even or an odd power. So if you think about an odd power, whether it be a cubic function or even a linear function that has an exponent of 1, and you look at these, I'm going to abbreviate here. If your leading coefficient of the whole thing is positive, it's going to take on a shape that looks something like this. So it's going to kind of be one of those. So a cubic function looks like that. A linear function looks like this. So notice it goes up as you read left to right. If it's a cubic or even if it's to the 5th power, it still takes on that similar shape. If it is a negative, what that negative leading coefficient is going to do is it's going to flip your graph vertically. And so it's going to reflect it, so it's going to look something like that. So it's going to just go the opposite direction. Instead of going up as you read left to right, it's going to go down as you read left to right. If it is an even function, or if it is an even power, and that power, that leading power is positive, think about a graph to the 2nd power or to the 4th power. It's going to take on that parabola type shape. And then you've also got, if it is to the negative, if it has if it is to the even power but it has a negative leading coefficient, again, it's going to reflect that vertically, so it's going to open out something like that. Now, keep in mind, depending on what the equation is, your shape might be slightly different, but your end behavior is going to be the same. And so as you look at this, notice here, your end behavior is going to go up on both of those if it is positive. So on the right, it's going to go up if it's positive. On the left-hand side, it's going to go down if your leading coefficient is negative. Notice it's going opposite directions if it's odd. So on one side, it's going up and down, and then on the other side, it's going up and down. If it's an even function, it's going the same direction. So if it's even, both sides are going up or both sides are going down. So as you're looking at these, something to keep in mind to kind of help you imagine what these things look like. We're going to talk about what if it's a negative power here momentarily. But first, let's look at this very first function. So you've got a function, and this is kind of an ugly one. This one's one of the more difficult ones, because not only is this going to be a a root, but it's also considered a power function because this fourth root is the same as taking something to the 1/4 power. So your power, notice it says to state the power, our power is 1/4. Our leading coefficient is 1/2. And notice that this has been vertically compressed by 1/2. So if we look at our original graph, if we type in 0, 0, and then if we had the fourth root of 1 is 1, and then if we look, the next one would be all the way out at 16,2. All right. And again, you can use your calculator for this, but because it's been compressed by 1/2, instead of going up 1, you're going up 1/2, and so it's going to look really, really, really close to that x-axis. Now, don't worry too much about the points, just think about your general shape. So this is very similar to a square root function, all right? Instead, it's a 1/4 power, and then it says to analyze it. So some things to analyze, if we go through our kind of checkpoints. Our domain, notice as we read left to right, 0 is included, and then it does go to positive infinity. Your range also starts at 0, and it does go up forever. It goes up slowly, but it will go on forever. Notice the next thing is continuity. So is it continuous? And it is, because we can draw that whole graph without picking up our pen or our pencil. So it is considered continuous. Increasing or decreasing behavior. So it is increasing, getting bigger as you go from 0 to infinity. It is getting bigger. Symmetry, so odd versus even, it does not have symmetry, so no symmetry. Okay, remember if it's even, it's going to be symmetric around your y-axis. If it's odd, it's going to be symmetric around the origin. It's going to have rotation symmetry. Boundedness, it is bounded below. It doesn't go below that 0 point, so it's bounded below. Local extrema, so do have a local minimum at 0, 0. And then you have the horizontal or vertical asymptotes. You don't have any asymptotes. And then the last thing here is end behavior. So we've talked about end behavior slightly before. So at your end behavior, that's where we're going to use those limits that we've talked about before. So the limit of our function, and you can write the function out, or you can just write f of x. So the limit of your function as x approaches infinity, as x gets bigger and bigger and bigger, so does your graph, even though it's slowly getting bigger. Now the other way, normally we would also have a negative infinity, but again, because this stops, it doesn't actually go towards negative infinity. So we don't need both end behaviors here because it only goes towards positive infinity. If this graph were to extend the other direction as well, then we would also have a second end behavior as x approaches negative infinity. Okay, so here's the deal. Let's talk briefly about what this looks like if you have negative exponents. So feel free to write this down if you want. But your negative exponents, if we look at this, so right now we have x to the -1. So notice it is in quadrant 1 and 3. I'm going to come over to my computer, so my voice is going to get louder for a second. If I were to change this to a 2, we're in the top 2 quadrants. We change it back to a 3, it's an opposite. 4, top 2. 5, opposite quadrants. So anytime we have an odd power, if it's negative, the odds will be in quadrants 1 and 3. Your evens will be in the top 2 quadrants, so quadrants 1 and 2. Again, however, if I change the leading coefficient to be negative, what that's doing is it's reflecting it over your x-axis. So it's reflecting it vertically. And the same thing is going to be true if I look at my odd exponents. So right now we're in 1 and 3. If I change my leading coefficient to be negative, now we're in 2 and 4. Okay, so it's still going to be reflected vertically. Okay, so anytime you have an odd, it's going to be in those corner quadrants. If it's a negative leading coefficient, it's going to be in the opposite corners. If it's an even negative, it's going to be in the top 2. If it's the negative leading coefficient as well, then it's going to be in the bottom 2. So hopefully that makes some sense there with negative exponents. All right, so moving on. Writing statements as a power function. So as you look at this, basically you're just reading it and you're translating the sentence into a mathematical statement. So the area So we have area varies directly. So we would have A equals, and then the square of the length of its sides. So then we have this square, so S squared, if we let this equal S. Now here's the thing, notice I left a gap, because you still technically have that constant of variation that we need to take into consideration. Okay. For number 2, the speed of p of a free-falling object that has been dropped from rest. So the speed p varies as the square root of the distance. Okay, so if you notice, you have p equals, and then you have this constant of variation given to you. So instead of k, we're going to have the square root of 2g, so that's my constant of variation, times the square root of the distance, so square root of the distance. Now, we could condense this if we wanted, because since they're both under the square root, we can go ahead and make that 2gd inside that square root. Okay, so that's just using the information in our sentences and translating it into an algebraic equation. If we look at a specific example here on the right-hand side, it says the power, so power is proportional. So we have P equals, and then we have our constant of variation, and then notice it says the cube of the wind speed. So we have V cubed. And then it gives us some information. If a wind of 10 miles per hour generates 15 watts of power, so this is our V, that is our wind speed, and this is our power, P. So what we can do is now we can use those two pieces of information to figure out our constant of variation. So I've got 15 for my P. I'm going to find my K, that's what we don't know, and then we can plug in 10 cubed. 10 cubed is equal to 1,000. And so to solve for K, I can go ahead and divide each side by 1,000. And so my K, if I simplify it, or we can leave it, either one, is going to be 3 over 200. Once you have that, you now have your equation. And so I'm going to rewrite this now using my constant of variation. So I've got P equals 3 over 200 times V cubed. And so notice, then it goes on to ask how much power is generated by winds of 20, 40, and 80 miles per hour. So all we're doing is plugging in here my 20, plugging in my 40, and then plugging in my 80, and you're going to get 3 different answers. So when you plug in a 20, you end up with 120. If you plug in 40, or you substitute 40, you get 960. And then last but not least, when you plug in 80, you get 7,680 watts. Okay, so those are going to be my 3 answers based on my equation. So again, to kind of recap those steps, you use the information in your question to set up your equation. Once you set up your equation, you plug in a pair of information that you know, so that in this case our 10 and our 15, to find our constant of variation, plug it back into your original, and then use that to figure out your new information. Okay. Last thing here that I just want to go over is how do you find a power regression model? So if you are using your calculator, keep in mind, not everybody has a TI-84, so you kind of have to play around with yours and figure it out. I'm going to try to get you guys some video links if you need it to help you. But those of you with the 84, what you're going to do is you're going to go ahead and you are going to go to Stat. And hold on one sec, got to go to my computer. You're going to go to Stat, and then you're going to go to, sorry about that, it's erasing that dot I just put there. There we go. You're going to go to Edit, and you're going to enter your information in those 2 lists. So if you look, okay, I'm going to try to move this here a little bit. What we have right here behind in that table, our average distance is going in our X or our list 1, and then the period of orbit is going in list 2. So to save us some time, I went ahead and put that in there. And then from there, you're going to go back to Stat, and you're going to go over to Calc. And once you get to Calc, you're going to scroll down and notice we have all of these different types of regressions. We got linear regression, quadratic regression, cubic, quartic, linear, natural log, etc. If we go down far enough, we find the power regression, which is what we want. It asks us which list is which. So we have the X is list 1, Y is list 2, so we're good. And then we let the calculator do the work. And notice we do have it in a power regression model. So our A is our constant of variation. Our B is our exponent. And so now when we look at this, Notice it says find a power function model and use it to predict the orbit period. So what we can do at this point is we can use the information we just got on our calculator. Our A was approximately 0.2, so that's our constant of variation. So f of x, 0.2, and then our exponent was approximately 1.5. Again, that information is coming from our calculator. Once you get to that, we're going to do some substitution. Now notice this is our x value, so 4,497 is going into our x value. So when we put this in, we get approximately 60,313 days, which then if you divide will give us approximately 165 years if you put it into years. Since it doesn't specify, you can use days or years for that. Okay, so that's quite a bit of information in just one little lesson. Obviously, if you have questions, ask. I will say this, the most important thing you can take away from today is this information in this corner, starting to understand the in behavior and all of that. Okay, so as always, guys, ask questions. If you have them, you're going to have plenty of time to work in class, so please don't hesitate to ask. Ask often, ask early. That way you can get stuff figured out. Thanks.